Hello and welcome back to BitLearn. This is where we break down complex technology into simple, powerful lessons. Because once you really understand the fundamentals, you can build anything apps, products, even your own startups. So let's get started. This is episode 6 of Electronics Made Simple or Electronics 101. And this episode is dedicated to a concept called adders. Let's look at it. So far we looked at semiconductors, we looked at NPN, PNP transistors, we looked at different ways of controlling current, voltage, resistors, so many concepts. But all of this does start adding up to a basic computer, and that's where the adder comes in. Let's talk about that. So computers are astonishing machines, right? They simulate physics, they render movies, predict weather, so many things. But beneath all this complexity lies an elegant and almost very simple truth. The truth is, nearly everything a computer does reduces to just addition. Yes, we talked about it earlier. You remember in the previous episode, we talked about how computers can do just addition and nothing else. So, yes, the computer can do addition. This is the same operation you learned as a child in your first grade. That's all it can do. So let's look into the details of how the complex operations are done with just addition. So addition is kind of the master operation of computing. It might seem exaggerated to say it is the master operation, but it's actually completely accurate. Nearly every computational process is built into it. Counting of events is addition, addressing memory is also addition, graphics is also addition, everything. But how do we do other mathematical operations? What about subtraction, division, multiplication? So, are we saying that computers can't do those things? No. I will tell you how everything breaks down into the simple concept of addition. So, the ability to add efficiently and do that millions of times per second is what transforms a simple piece of silicon chip into a big thinking machine. So, before we understand how a circuit adds, we need to understand what exactly is adding. So for that we need to talk the language of binary, the language of digital circuits. So all digital electronics speak only one language, binary. A circuit at its lowest level can only see a high voltage or a low voltage. High voltage can be treated as on, low voltage can be treated as off. So high can be treated as 1, off or no voltage can be treated as 0. Nothing in between. If we go with that kind of a assumption, then it's much easier to build electronic circuits. If you remember the previous episodes, we could have gone to, instead of binary, we could have taken the whole decimal system and looked at different voltage values. It just makes things very complex at the electronics level, and also makes it very error prone, because if you're measuring a specific voltage to say whether the digit is a decimal 6 or a decimal 8 or 9, you basically run into trouble. Instead, it is much easier to say whether you have a current or not. If you have current, it's 1. If you don't have it, it's 0. So that is much easier to manage at electronics level. So that is how most or all digital circuits think only in binary. So now let's get to the topic of addition. So addition in computers is now stripped down to its simplest form, adding two single bits, 1 and 0, because that's all it understands. And thankfully, binary addition has only 4 possible outcomes. 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is also 1, and now comes the interesting case. 1 plus 1 is equal to 1 0. This is not your decimal number 10, this is 1 0, 2 bits. So it basically, the sum is 0, but we also get a carry of 1. Just like adding 9 plus 1 in decimal, it generates a carry in decimal, right? If you add 9 plus 1, you get a 10. How is the 10 represented? It's a 0 and a carry of 1. So this pattern of sum plus carry, this forms the DNA of digital arithmetics. Every circuit we build from here must be able to produce both. So let's look at it. It must be able to produce a carry and a sum. So the first one we look at is the half adder. This is the simplest adding circuit. To add two single bits and produce a sum and a carry, digital electronics uses the half adder, the smallest or the simplest possible addition circuit. It takes two inputs, A and B, and produces two outputs, sum and carry. So why does this work? Let's look at it. So if you look at it carefully, the sum behaves exactly like a XOR gate or a XOR gate. So the carry behaves like an AND gate. So let's look at that. All the half adder is doing is it has one XOR gate and one AND gate. This tiny circuit is an extraordinary example of digital elegance. With two gates, we reproduce the fundamental logic of arithmetic. But as powerful as it is, the half adder has a problem. There is a limitation. Imagine adding two multi-bit binary numbers. So far we talked about just 1 and 0. It was able to add that. If you have a multi-bit binary number like what you see on the screen, uh, the least significant bits must produce a carry that needs to be added to the next pair of bits. But the half adder has no way to accept a carry. It only knows how to add A and B by themselves. So that is why it's called a half adder. It only solves half of the real problem of addition. To add multi-bit numbers, we need a circuit that can handle three inputs. Basically, it can handle A, B, and if there is a carry from the previous column, it should be able to add that as well. So that brings us to the next evolutionary step in adders. It's called a full adder. This is the real workhorse of arithmetic. A full adder handles the complete logic of addition for a single bit position in a multi-bit number. So it accepts A, it accepts B, and it also accepts a carry in. So which means you can chain together a bunch of these adders, and whenever there is a carry bit, you can pass it to the next adder that will take that as the carry in, and it will add the next two bits A and B. So, and it also produces sum and carry out. So you can chain a huge set of full adders together, and you can do multi-bit addition quite easily. So inside a full adder, there is this clever part. It is constructed using two half adders and an OR gate. The first half adder basically adds A and B. The second half adder adds the sum from step 1 to the carry in, and the OR gate merges the carry outputs of both half adders. So this modular construction is not only just elegant, it mirrors the logic of human arithmetic. When you are adding digits, you also take the carry and add it. You also determine whether a new carry is generated. So that kind of summarizes how a full adder works. Then we have one more advance, we call it ripple carry adders. Now that we have full adder capability of handling one bit and a carry, we can simply chain it together. We simply repeat these adders, and what we get is a chain of these adders. For 4-bit addition, you chain 4 full adders and you get a ripple carry adder, and the carry out becomes the carry in of the next. So this creates a ripple carry adder. A circuit where the carry value ripples through each stage like falling chips or dominoes or whatever. It's simple, reliable, forms the conceptual foundation for most advanced adders used in modern CPUs. But even in those advanced design, the underlying logic remains the same. So let's look at the power of these simple building blocks. It's kind of remarkable to realize how much of modern computing is built from such tiny constructs. So from these basic circuits, we can build XOR, AND, OR, half adders, full adders, everything. And you can make much more complicated components like ALUs, floating point units, GPU shaders, all of those things. Now let's look at the elegant trick behind subtraction. We said the adder can do just addition. Now let's look at how do we do subtraction. Here is a twist. Computers almost never build separate circuits for subtraction. Instead, they use a brilliant method called 2's complement, which transforms subtraction into addition. This trick allows the same adder hardware to perform both addition and subtraction without extra circuitry. You can look at the 2's complement details in the previous episode. We talked about what exactly a 2's complement is. So that's about how an adder works. The conclusion, the idea is simple. Most of the complex electronics that we see is actually made from very simple ideas. I had to make a short episode on just these adders to tell you that most of the complex CPUs, all the algorithm units, everything that we have, ALUs, graphic shaders, everything is built on this basic concept of adders. Chaining those circuits kind of gives birth to complete arithmetic. So that's all you need to remember. I know that this is very much at a very high level. I just wanted to bring awareness. You can go into details of how each of these things work. Like for example, if you wanted detailed episode on what is 2's complement, how do we get 2's complement to act like subtraction, we can go into that. But meanwhile, it's just enough to be aware that everything in computers is just addition. That's the beauty. Adders are more than circuits, they are the pulse of every digital device. So mastering them means understanding not just how computers work, but why the digital world is built the way it is. I hope this kind of pokes you and makes you more curious to learn more. So go ahead and you can look at some of the textbooks on how all of these things work. So meanwhile, do subscribe, leave a comment below, and come back for the next episode. Thank you for watching.